Okay, I'll get started. I noticed that last time I announced that I'd have an oral exam and then bam, 14 people at the start of the lecture. But I have not just announced that I'm having an oral exam, so there are fewer people at the start of the lecture. I assume they'll trickle in later on, but things that I say at the beginning are also generally important. I want to say a few more things about the oral, but first, are there any questions?
Are we going to have lecture next Tuesday, or is this our last lecture class?
This is our last lecture. I have thus far, I'm supposed to be doing research apart from this. And every single week I go to my advisor on our weekly meeting and I say, like, I can't, I've just been busy with the class. I guess I'm busy next week because of the oral as well. And grading, lots of grading, but finally I'm free. This is the last lecture.
Okay, thank you.
I'm sure you're all relieved as well. Oh, also, can everyone please complete course evaluations? That's very important for me. Are they still open? I haven't actually received an email about them.
I haven't received email either.
That's really weird. Yeah, that's weird.
Do you have to do it on Blackboard or is it another website?
No, usually you're supposed to get an email. I also get an email every single semester asking me about the questions that should be on course evaluations. Course evaluations are never supposed to happen after the final exam goes out. You know what? I'm going to send an email and ask about this because this should be a normal thing. Plus the response rate is going to be much lower after the course is ended. So if you haven't gotten an email about it, that's really weird. Okay, thanks for letting me know. I was also really, it was really odd that I didn't get an email about it either. Okay, I'll definitely look into that. Any other questions? Right. So let me just say some general advice for oral exams. These are some really obvious points in retrospect, but you might not realize them at first. So these are, this is oral exam advice. Number one, so on the pre-oral basis questions that you submit, it is much better to submit a blank problem than work that you don't understand.
If we don't understand it, is it okay to at least attempt it to what we think is like right and try to maybe so you can understand our mindset?
Yeah, so the thing is, imagine this. Let's say if you submit absolutely no questions about trig substitutions, I'm going to look at your exam paper and I'm going to conclude that you don't understand trig substitutions, and that's fine. And I'm not going to ask you questions about trig substitutions. So you're setting yourself a bit behind at the start of the exam, but on the exam, you're not going to be asked questions that you're not able to answer. On the other hand, you should understand the solutions that you're submitting. If you're writing stuff and you're not sure whether it's correct in like a very strong sense, you don't know whether one line follows from the next, then you're doing yourself a very strong disservice because I might ask you about it on the exam. And then what are you going to do? There's only a 20-minute exam. You don't have much time to, you're supposed to do impressive things during the exam. And if I spend some time discovering that you don't actually understand a solution that you've written, well, then time has just been used up and you're back. If you, on the other hand, so that question counted against you as a whole. On the other hand, you leave blank and I just don't ask you about it. So never pretend that you understand something which you know that you do not understand. And similarly, it's very good to be very honest directly. So if I ask you about something and you 100% know that you don't understand it and you don't want to attempt an answer, then immediately say that you don't understand it as opposed to attempting to BS. Because again, time gets wasted and you have very little precious time on the exam.
That's also good advice for a job interview.
Yes, that's a really good point as well. Yes.
What if we
So
have the wrong
when you're-
answer? Do we still get like points with you? Like if we defend an answer that we got, like, but it's wrong, like we explain our process in getting there, or is that just
Yes.
not worth anything?
So it's the solution is this process of your solution is more important than your final answer. And I'm not going to ask you to like do a full question on the spot on the exam. If you know the general strategy that would go for that question, then that's good. So for example, you say, I would do this substitution here, and I think that this might work. And then we can discuss whether that would work or not.
Okay, thank you.
So if you've made like an algebraic mistake, that's fine. So it's not like the fact that you're worried about the fact that you might have made an arithmetic mistake somewhere means that you should submit a blank, you should submit a problem blank. You shouldn't leave too many problems blank either, because that just tells me that you don't understand that material. And then I'll just accept that you don't understand that material, and that will be an agreed upon thing between the two of us for the exam. So you're not, again, my goal in running oral exams is to be able to rank you all. So I know that not everyone is going to understand everything, and I know that a lot of people understand a certain number of topics, but they don't understand a certain other number of topics. So that means you can't be in the top few places on the ranking, but that means you might have a good exam with the material that you understand if you submit the right things.
I have a question.
Right, and go ahead.
I'm a little bit confused. So like, are we gonna do an exam and then take an oral exam where you pose us a question and then we have to tell you the thought process of the question of how we would solve it? Or like we'll tell you the thought process of like the questions that we answered before. Like I'm kind of confused.
I am not going to grade what you submit in written form, but I am going to spend the time between exams reading your submission. And I'm going to ask you questions about it, but not exclusively about it. I might also say, well, what if I took this problem and I changed it up a bit? How would you approach the problem then? And I'm not going to ask everyone the same questions. In particular, I'm going to look at your paper and then I'm going to choose what questions I'm going to ask you about. So I'm going to choose specific things which stand out to me on the paper, and then I'm going to ask about those things. It's really easy for me, like if you leave a question completely blank, I'm not going to ask you about that question because it's obvious that you don't understand that material if you haven't submitted those problems, and I can easily waste 20 minutes of time, but that would be cruel, and I'm not going to be cruel on the exam. But if you submit poor quality answers, then I might actually pick at your reasoning for those problems.
Okay, that makes sense. So if you submit good quality responses, then you just explain like the work that you did to.
Well, I'm going to ask you questions, so you shouldn't. But yeah, I might ask you to. So the exam is the paper is going to have some easy questions and it's going to have some more difficult questions. If like the first problem is probably going to just be to integrate a polynomial because that's a really easy problem. And more than, well, at least 80% of the people in this class will just solve that question correct right away, just integrating a polynomial, right? And then I won't ask you to explain how you integrated a polynomial because that's just wasting time on the exam. On the other hand, one or two people will actually integrate the polynomial wrong, which means that the level at which I'm going to start the questions is much lower for them than it is for other people, right? So if you have a bunch of easy questions which you solve perfectly, I'm just going to accept that you solved those questions perfectly, and then I'm going to start the exam at a higher level, which means that you can do more impressive things during the exam, which means that you leave a more favorable impression and get ranked higher.
Just a question, which would you say is better, starting at a lower level and getting everything right, or starting at a higher level and getting everything wrong?
Well, I'm not going to start at a level where I'm not going to start at a level that's too high so that you get everything wrong. And if I notice that you're doing poorly, I'll, on the first 1 or 2 questions that I'll ask, then I'll move the level below. So I do not think that you should game the system. I think that you should do your absolute best on this. Absolute best on the written submissions. With some things kept in mind. And the things kept in mind are that you should ensure that you understand the solutions that you submit. If you do not understand a solution that you submit, then that's bad. But beyond that, it's better for you to do your best job on the written submissions. And again, that really comes down to my ability to run the exam. I'm supposed to run it in a way in which it's more advantageous for you to do your best job rather than set the bar low. And I will figure out how to do that. I'll spend a lot of time thinking about it this weekend. And after the first maybe 2 or 3 exams, I'll have proficiency in this. Okay, point number 2. You may think when you're studying for an exam that you should study the hardest material and the material that you don't understand to the greatest extent. This is wrong. You shouldn't study the material which you understand at least. You should ensure first that you understand the basics. So study the basics first, not what you understand least. So again, my goal in this exam is to see whether you understand some material. And I want to know how much you understand and how well you understand it. Now, you could sort of spread yourself thin by having a somewhat competent grasp on the basics, but with a bunch of holes, and then you could spend all the rest of your time studying other more advanced material. Well, if I get the sense that you're shaky on the basics, then I'm going to ask you questions only about the basics, and all of the other material that you spent studying, well, that's not going to help you in the least. So you should ensure, prioritize having a core of material that you understand very well. And then all of the material at the end, you can even forget about the last several topics. Most of the material on assignment 5 isn't going to be, I'm not going to ask questions about homework 5. But I am going to ask some volume problems. Volume problems are good, and they're good questions to ask you to set up without solving the integral. So prioritize, let's say, owning, in the sense of you feel that the material belongs to you, you understand it in a very deep level. A core of material, the core, some core of material. And the more you understand, the better it looks. But I'm going to ask you questions at like the last point at which you understand the material well. If you have, so don't study the thing that you understand least if you still have issues with material that comes before it. And this is counterintuitive because on other exams that are not oral exams, that are written exams, the weight of each question, you might have just questions appearing on that topic and you don't want to get a 0 on those questions, right? So it makes sense to spread yourself thin so that you can answer, because there's just a threshold of whether you're able to answer the questions or not. And so you don't want to like be in a position where you only understand half of the material and are only able to answer half of the questions on the exam. Well, that's not the case for oral exams. Because I'm not going to ask questions about everything, and I'm going to ask questions relative to what you understand, and I'm going to get a sense of what you understand based on what you submit. And did I have another piece of advice? I had a third one. Well, I guess Okay. I was speaking to one of my two advisors today, and he gave me two pieces of advice. This was one of them. I don't remember his other one, but I will also just say this, be quick to admit what you don't understand. And again, oral exams are completely immune to BS, no BS. This just does not work on oral exams. And then if you haven't signed up, I've sent the link, so be sure to do that. Also, I'm surprised that everyone took the Wednesday slots first. I said a few things to sort of prompt people to take the Wednesday slots. I mean, on Thursday slots, you get extra day to study. So I was like, I have to tell people to take some Wednesday slots, and then bam, suddenly all the Wednesday slots got taken. So yeah, the disadvantage of Thursday is that I'm a more experienced examiner. And having an inexperienced examiner gives you some advantages because I'm going to be making mistakes at the start. But later on, I'm not going to be making mistakes, and then I'm not going to compensate for that. But like the effect disappears halfway through the Wednesday. So, but anyway, when all of the Wednesday slots are taken now, which I'm happy with. That's good. Okay. So I have a tiny bit of material that I want to cover today that's left over, and then I'm going to spend the rest of the lecture doing review. Any questions before then? Last ones?
I just have one more quick question. When do you expect us to get our final grades? Is there like a deadline that you have to have them in by?
I get stern emails at some point. I don't get in trouble if I don't submit them by a certain point. I think that I'm going to aim because I don't want this to drag on forever. To have grades in within a week after the end of the course. So after the exam, give me like a week to grade everything that's outstanding and do my process. And then I should put in grades. I think that I personally, for myself, do not want to have this drag on for more than a week after the end of the oral. So most likely.
Sorry about that.
Go ahead.
I was just gonna ask, would you recommend that we like study the midterm questions and solutions for the oral exam, or the assignment questions and solutions?
Well, the midterm should reflect, is very similar to the assignments, was it not?
It was. I was just saying because it's spread out a little bit from assignments 1 through 5, and
Right.
we didn't get the grades back fully, but we kind of know what we did because of the solutions. And assignment 5 just dropped, so that's what I was asking.
Okay, yeah, let me tell you this. So a few more facts. Facts about exam coverage. So first off, I'm going to let Riemann sums die. We've already done enough of this. Riemann sums, I've belittled you enough with this, or belabored Riemann sums enough. So, okay, I'm not going to have Riemann sums questions on the exam. In other words, the homework 1 material and homework 5 material aren't really going to be on the exam. Now, if you look at what homework 2 and homework 3 are, then there are a bunch of integration problems. And if you look at what homework 4 is, then it's a bunch of volume and area problems. And that's what's going to be on the exam. And so you should study these solutions from homework, and I'm going to post homework 4 solutions soon. You should study the solutions from homework 2 to homework 4. And you should study the midterm solutions. And the midterm solutions, the only difference is that it doesn't cover homework 4, right? But the midterm is very similar to homework 1 and homework 2. But you, we've done Riemann sums to death. I wanted people to get Riemann sums. Some people got Riemann sums. A bunch of people did not get Riemann sums. It appeared already on the midterm, and for all of the people who didn't get it on the midterm, me putting it on the final, no one would understand anything else. So all of the people who didn't understand it on the midterm won't understand it on the final, and all of the people who understood it before already understand it. So it's just, it's suboptimal to include Riemann sums questions at this point. We've done it to death. On the other hand, what I do really want you to understand is how to integrate. And in my review session today, I'm primarily going to talk about how to integrate. Actually, I've prepared absolutely nothing about volume problems because sort of that material is fresher and you can go through that lecture again. I'm just going to go through integration techniques. Okay, and what else do I want to say? Well, actually, yeah, homework 1 and homework 5 aren't really going to be on the exam. And I think that's all I want to say. Okay, I'll say this. I am a bit overly fond of trig substitutions.
Would you say it's better to do well on the final? Say that we do better on the final than we did on the homework assignments that we submitted pertaining to the final. Does it kind of like cancel out your poor homework assignments? I don't know if I'm asking that question in the correct way.
It does. I consider everything when I grade. I mainly want to see people do some impressive things. So I think that if you do, if you have equal performance versus you transfer some performance from one component to another component, then despite the fact that the numbers might average out, it's more impressive to have better performance on one piece of work than another bad performance on another piece of work, because mediocre performance means you understand it to some level, but strong performance means you've really understood something. And that's a lot more meaningful for me than a series of mediocre performances. So the answer to your question is yes.
Okay, awesome. Thank you.
Mhm. Okay, and I think that's all that I have to say. I'll send, oh, right, I'll release the questions. The basis, I'll call them the basis questions. These will be released on Monday. Let's say at noon. And they will be due on Wednesday at 11 a.m. In other words, prior to the first exam. That's when exams start. So everyone has to have their questions in before the first exam starts. And that's just for the sake of fairness. I personally would have like almost been fine with just having it in before your exam, but it incentivizes taking an exam on Thursday much more than on Wednesday, because you get an extra day to work on the basis problems. So the only fair way to do it is this. So you have more time to work on those problems than you did on the midterm problems. And remember that this is semi-open book. In other words, you are not allowed to use any external resources. Whatsoever. And by you can use the course resources, the lecture videos and everything on the websites. So you are not allowed to use anything not covered in class. You can only use methods covered in class. That fits with the semi-open book formats. In particular, there are many things that did not count as cheating on the midterm, but that involved just finding a static resource which had similar questions and using methods that are not covered in class and then just using overpowered results to solve it. And that was bad. That is not what I wanted. And I'm explicitly prohibiting this by making the exam semi-open book. So the standard of arguing and presenting clear solutions is the standard that has been adopted in this course. And that is the material that you should be consulting in preparing for it.
Can I ask one more question? When
Yep.
would today's lecture that you're doing be available? Since you said you're going to go over it and integration techniques, I want to like get a good study time with this lecture too.
I'm going to post it tonight once I get the link. So it takes like 2 hours for the link to get formatted, and then I get sent it. And I'll post the slides onto the course website soon. Okay, but yeah. So is that everything? We should get started.
Yes, thank you.
Half an hour. Go ahead. Okay, so very quickly, I'm going to wrap up the material before we get on to the review lecture. I'm going to give another example of an improper integral. So say I consider the integral from 0 to 3 of 1 over x minus 1 to the power of 2/3 dx. So what happens here is, where is this function not continuous? Where's the problem point?
At x equals 1.
Yeah. So what I need to do is that there are two ways to approach the problem point. And so I need to consider two separate integrals. I need to consider the limits as b goes to 1 from the left. Of the integral from 0 to b of 1 over x minus 1. It's the 2/3 dx. And then remember that I should keep writing limit. If I've written limit once, I need to keep writing it until I actually get rid of the limit. What is the antiderivative of this function? So remember that this is x minus 1 to the minus 2/3 power, right? So how do I integrate that?
Use u substitution.
Yes, you can. You can substitute x minus 1, but let's suppose that you had x to the minus 2/3. What's the integral of this? If it were just x to the minus 2/3, then what would the integral be?
Power rule.
So what do you get?
Negative x, oh sorry, x to the minus 2/3 minus 1.
Do you add or subtract 1?
Oh, sorry, add.
So what does the exponent become?
3 negative 1/3.
Or it's 1 minus 2/3 is 1/3.
Oh, sorry.
And then what's the prefactor?
Would it just be 3?
Exactly. You divide by this, and so you get 3. So the antiderivative of this one, you can do this by inspection. You would shift it over, and you still get x to the x minus 1. It's the power of 1/3. And then we evaluate this from 0 to b. And so what that gives us is the limits as b goes to 1 from the right of, now if I put in b, I get 3b minus 1 to the power of 1/3. And then b, when I put in 0, I get minus 1 to the power of 1/3. And that's minus 1 times 3. Now, as b goes to 1, what does the left expression approach? If we were to draw the graph of x to the 1/3, then it looks like sort of like the square root function. Well, it looks like x cubed tilted on the side, right? So as b goes to 1, this argument approaches 0, and the cube root of it approaches what?
Would it also be 0?
Yep. So we get 0 minus minus 3, and that's 3. And then the key point here is that you have to do both of these separately. And then if I rewrite the expression again, it's a bit tedious. I get, so here I get 3 minus 1, that's 2. So that's the cube root of 2, 3 times the cube root of 2. And then I get minus 3 x b minus 1. So the 1/3. And once again, if we look at this limits, b is going to 1, so that term is going to 0. So that's equal to 3 times the cube root of 2 minus 0. And so as a result, the integral from 0 to 3 of 1 over x minus 1 to the power of 2/3 is equal to 3 plus the cube root of 2. Because by definition, this integral is the sum of these two from the definition that we made last time. You could sort of write it in this way, or you could just write it directly. You've evaluated both of these. So the way this works as mathematical sentences is we start off the problem, then we make 2 observations. We make an evaluation of this limit, we make an evaluation of this limit, and then we put it all together and make this statements. And it follows from these 2 statements.
Could you explain again why you have to evaluate it, approaching the 1 from the negative side and positive.
Right. Because we can consider, for example, the integral from 0 to 3 of 1 over x minus 1 dx. Are you asking why I didn't just take the antiderivative and then plug in both values at the endpoints?
Yeah.
Right. So in this case, let's do the naive solution. Well, I mean, we know that the antiderivative is logarithm, and if we look at this expression, it blows up to infinity, right?
Yeah.
Now, naively, and this is wrong, we could say that this is equal to the logarithm of x minus 1 evaluated from 0 to 3, and then gets the logarithm of 2. I may as well remove the absolute value bars. And then when we put 0, we get minus logarithm 1, which is logarithm of 2. This logarithm of 1. Why am I writing? Okay, I should be consistent with my notation. Sometimes I don't write that in this class. And that's wrong. So you get a result that's false. There's another more subtle reason, and that's that antiderivatives, if the antiderivative isn't defined globally, you can actually take the function and you can move it at different pieces. So logarithm, let's consider the function f of x equals the logarithm of x when x is greater than 0, and it's equal to logarithm of negative x. And then I add 5 to it. So I add a constant on one piece, but not on another piece. This is also an antiderivative. So if it's a discontinuous domain, then I could make the antiderivative. I could add a constant to only one part of it, but not the other part. And you can see that you get a completely different answer here then as well. So it just doesn't work. The fundamental theorem of calculus does not apply when there's a hole inside of it. That more subtle reason, it can give you a wrong answer here as well. Because the constants would cancel out here, and the constants would cancel out here. But if you just took one limit and the other limit, the constants would be different. And aha, now you're in trouble.
Okay.
So both of those reasons are primarily theoretical. The theorems that you're using to evaluate the antiderivative do not apply. And you will get an answer of log 2 here, which is just wrong. The actual answer is that the integral diverges.
Okay, thank you.
Actually diverges.
So as far as like the limits that we calculated, the reason why we did that is because there was like a value of x where the limit doesn't exist, so you evaluate it from the left and right.
Yes, it's a place where the function blows up, so the function is discontinuous at that point. Well, it doesn't have a value at that point. And the thing is that we can evaluate integral from 0 to b when b is less than 1, because the function is bounded on that range, right? Everything is good. Whereas if you put the integral from 0 to 1 without a limits, then the function isn't bounded on that range. So the integral isn't even defined.
Okay, so because of that gap, we need to set up two limits from the left and the right, and then you
Exactly, and that's the main point about improper integration.
So can I ask another question? So that's because from 0 to 3 exists 1, and if you plugged in 1 for x, you'd have an undefined function. Yeah. Okay, got it. Thank you. So if it was from 3 to 5, range from 3 to 5, then you wouldn't have to do that.
Yeah. Okay. 3 to 5, you have a continuous antiderivative. The function is bounded everywhere, so that's
okay.
nice.
Yeah. No, that answers my question more directly. Thanks.
Right. So that's a good example. If for integral from 3 to 5 of 1 over, so x minus 1 to the 2/3, you just do the antiderivative.
And just to clarify, the final answer is 3 plus 3 cube root of 2.
Exactly.
So you would add both of the limits together, whatever you solve for.
Exactly. And if I open up last class's lecture, so I can open up that up here, you'll notice that I, for example, have this table right here. These are definitions. If f is bounded on every closed subinterval of a to b less a point, then by definition, the integral from a to b is the sum of these two limits.
Oh, okay. So that's kind of like the outline for how to solve all of these kinds of problems.
It is, but not only is it that this table right here gives meaning to those integrals, because before I've written out these definitions, that integral was undefined. What we defined integrals of were functions that were bounded on closed intervals, right?
Mm-hmm.
And this function is not bounded on a closed interval. It's not defined at one point, and it's not bounded on everywhere else where it's defined, but it's bounded on any closed subinterval of this. And so these limits make sense.
Oh, okay. Okay.
Well, rather the limit, we're taking a limit of an expression that makes sense. This is always going to be a number under the hypotheses. The limits may or may not exist.
Okay, gotcha. Thank you.
Good. So the main lesson is if it's a point in the middle, or if you have the integral from negative infinity to infinity, if there are two divergences in any way, you have to split it up into multiple integrals, and you have to evaluate each part individually. And that's because if you don't, you might have what you're really hiding here is infinity minus infinity. And infinity minus infinity can be made equal to any value. Okay, the very last topic of the class is on comparison tests. And I put some questions on the exam. So I am admittedly doing both improper integrals and comparison tests just because they're a usual part of the course material. I won't actually have these on the final. The final will focus on the core material. But you should know these, and they're going to be important in calculus for Calculus C. So first off, as a side remark, is that if f is integrable on closed all finite closed subintervals of its domain, which, for example, f is continuous. Except at some points, except at as with asymptotes. Then the integral of whatever bounds you have, or you know what, I'll just write it like this. I will write all of my integrals as 0 to infinity, but really I mean any improper integral that you might consider. Then this integral converges if and only if the integral of the absolute value of f of x converges. So when does an integral converge? Assuming that it's not a question of it not being integrable in some stronger sense. It occurs when there's only finite amount of area under the curve in an unsigned sense. So if you have infinite negative area and infinite positive area, then those can't cancel out. So if you convert all of the negative area to positive area, then it's just a question of whether there's finitely many of it. So the sign, assuming that the function is integrable in the first place, the sign does not change whether improper integrals converge or not. So that's just a side remark at the beginning, and that's going to let me state the comparison tests in a slightly different way. So the first comparison test is the direct comparison test. And what this says is that if, let's say, 0 is less than or equal to the absolute value of f of x, is less than or equal to the absolute value of g of x, you know what? I'm actually going to make those integrals be not from 0 to infinity, but from a to infinity. It's slightly more general. But I really mean any type of improper integral. Then if the integral from a to infinity of g of x dx converges, then what can I conclude? So if g is an upper bound of f on, let's say, a to infinity, and if the upper bound converges, then what's about the smaller function? Well, it's the obvious statement. What is the obvious statement?
Then it's like integrable.
Yes. Well, it converges. So if there is only finitely much area here, then integral a to infinity of f of x dx converges. And by the way, I should write one more thing. This is assuming f and g are integrable on AB. Or equivalently, I could replace this hypothesis with saying that f and g are continuous. That would be a slightly weaker theorem. So you could have functions that aren't integrable at the outset just because they're too crazily behaved, where taking the absolute value would fix that. So we should be careful in saying that the functions are well behaved originally. But if they are well behaved originally and the upper bound, this improper integral converges and the lower bound converges. And similarly, if the integral, the lower bound from a to infinity of f of x dx diverges, then what?
Then the integral a to infinity g of x diverges.
Exactly. So this test is very often useful for showing that an improper integral converges when you can't evaluate that improper integral directly. So to give an example, here, does integral from 1 to infinity of sine x divided by x squared dx converge? Now, what integral are we going to compare it to? So remember last time, last lecture, we talked about what was called the p-test. We considered as to what would happen. So this is called the p-test for this integral, right? Integrals of the form 1 over x to the p dx. And we said that this converged if p was greater than 1, right? So you're allowed to cite this and call it the p-test. So what integral do we know converges by the p-test?
Integral of 1 to infinity 1 over x squared.
Exactly. So notice that we have that the absolute value of sine of x over x squared, this is less than or equal to the the absolute value of 1 over x squared, although the absolute value bars are redundant because the absolute value of sine of x is less than or equal to 1 always, right?
So why are the absolute value bars there again?
The absolute value bars are there just because of the statement of the theorem. By the way, this 0 less than or equal to is redundant as well because I put absolute value bars. So I'm just putting it there for the sake of stating the theorem, right? They're necessary for this one because sine is sometimes negative. So if you have a very big negative number, then it's less than a positive number, a small positive number, right? So an absolute value f might be bigger, but if you didn't include the absolute value bars, then you might be misled. Remember that and having finite area in an unsigned sense only relates to whether there's finite area for the absolute value bars, absolute value version of the function. And here, this is sometimes negative. And the theorem has absolute value bars in it. So I'm just verifying that the theorem holds, right? Now, as you said, the integral from 1 to infinity 1 over x squared dx converges by the p-test. Thus, by the direct comparison test, we can conclude that's the integral from 1 to infinity of sine of x over x squared dx converges without evaluating it, right? And so this is how I'd write up the solution. This is the question, and that is the solution. Now, similarly, what if I ask, does the integral from 1 to infinity of 1 over the square root of x squared minus 0.1 dx converge? What integral am I going to compare this to?
One over root x?
Well, 1 over the root of root x or root x squared.
X squared.
Yep. Which is also known as the integral from 1 to infinity of 1 over x dx. And what do we know about this integral? By the p-test again.
It diverges?
Yes. So it converges only when p is strictly greater than 1. But here p is 1, so it diverges by the p-test. Now, what do we do? Okay, there's a question, and what exactly converges means. So here is what I mean by converges. Previously, going back to the previous lecture, we noted that when you have an unbounded function or when you have an infinite domain, so for example, here were the definitions for infinite domains. Yeah, here, if you had unbounded ranges, then the integral from a to b makes sense. That's a number, right? Well, the integral right here, we're not guaranteed whether it's a number or not. And so the very definition of what this integral means is that it's a limit. And then the reason that I say converges or diverges is because the limits in the integral can either converge or diverge, right? And then, for example, if you have negative infinity to infinity, it's two limits. And for the integral to converge, both limits have to converge to a number. So because the definition of these types of integrals involves a limit, there's a possibility that that limit can diverge. Whereas if a function is integrable on an interval a, b, then we know that the integral is going to be a number. That's guaranteed already. And we know that if we look at under the assumptions, that's the integral within here, all of these are going to be numbers. But the question is the limits of those numbers a number? And that might fail. Does that answer your question? And I mentioned before that if we think of the integral as a measure of area, then if there's an infinite amount of area, then the integral shouldn't converge. And so with this integral, for example, the antiderivative is logarithm. And if we look at the limits of the function evaluated, the antiderivative evaluated at the upper end point, log of b goes to infinity as b goes to infinity. So this integral doesn't converge. Now, can we do a comparison? Well, if we look at 1 over the square root, so this looks like assignment 1 of x squared minus 0.1, or let's write it like this. Square root of x squared minus 0.1. This is less than or equal to the square root of x squared, because the square root function is increasing, and here we're subtracting something. And so when we divide, we get that 1 over the square root of x squared is less than or equal to 1 over the square root of x squared minus 0.1. And thus, now the integral from, and I should write 1 over x equals, the integral from 1 to infinity of 1 over x dx diverges by the p-test. So by the direct comparison test, the integral from 1 to infinity of 1 over the square root of x squared minus 0.1 dx diverges. Because if we look at what the lower bound is, then it's less than or equal to this one. And I can put absolute value bars everywhere as well, because the theorem technically speaks about that.
Wait, so the well, after the well part, what is that saying?
Well, so square root of x squared minus 0.1 is less than or equal to the square root of x squared, because here I'm taking the square root of a smaller number, right?
Right, are those like, comparing the lower bounds? You said?
Well, before I divide by the its, I'm going to just state this equality. So this is a mathematical sentence, right?
Yeah,
This is a true sentence for every single value of x. And I can
Okay.
derive another sentence from it. I can divide by both of these. And if you're dividing by a bigger number, you get something smaller, right?
yeah, okay,
And now what are these things? Those are the original functions that I had, right?
yeah,
So I've established an inequality of the functions, and I know that the lower bound diverges, so the upper bound has to diverge as well.
right, okay.
So this is the direct comparison test, and I've used it to show that something converges, and I've used it to show that something diverges. Now, notice that, so to motivate the next example, if we considered the integral from 1 to infinity of 1 over the square root of x squared plus 0.1 dx, then the direct comparison test does not help. So it's completely useless for handling this situation. And it's not a very powerful test, right? Because now the inequality goes in the other direction. But if we want the lower bound to diverge. But here, 1 over x is the upper bound. So that motivates having a better test. And this is called the limit comparison test.
Wait, can you explain that one more time?
Right. So how did this argument work? This argument worked by saying that this diverged because a lower bound for it diverged, right?
Yeah,
Now, why was this a lower bound? Because we were dividing by a smaller number here, right?
right,
Now, what if I change the problem slightly? What if I change the minus to a plus? Well, now I'm dividing by a bigger number here. So this function is in fact smaller than 1 over x.
oh, okay,
So what are you going to do now? Your argument fails, right?
right, okay,
So that's an issue with the direct comparison test. It doesn't get very far. And there is a better comparison test that you can use. And that test is called the limit comparison test.
sorry, so it fails because it's not agreeing with that.
Well, we want a function that's smaller than it to diverge, right?
Right, yeah.
But the natural function that you're comparing it to isn't smaller than it.
Oh, okay, so you're trying, okay, that makes sense.
Now, how do you fix the situation? You fix the situation by using a different comparison test, the limit comparison test. And how does the limit comparison test work? Well, if you have, if the limits as x goes to infinity of f of x divided by g of x is equal to L for, let's say, 0 is, you know what? I may as well put absolute value bars. Okay, it doesn't matter. Sorry, 0 is strictly less than L, is strictly less than infinity. Then the integral from, let's say, a to infinity of f of x dx converges if and only if the integral from a to infinity of g of x converges. So what does this say? This says that if in the limits, the functions are approximately a constant multiple of one another, then this integral converges if and only if this integral converges. And again, under the assumption if f and g are nice. E.g. continuous. You can have situations where f isn't even integrable in a stronger sense, but as before here, we said something along the lines of if assuming that's they're integrable on any closed interval AB. So the same sort of niceness criterion applies, but if the functions, for example, are continuous, then that's good enough. Any questions about the statement? So to give an example, let's see that it solves the previous example that we had. If we have the square limits for the integral from 1 to infinity of 1 over the square root of x squared plus 0.1. That was the pesky integral that we couldn't solve last time. Well, we're not solving it. We're trying to show that it converges. Then what we're going to do is we're going to compare this to the integral from 1 to infinity of 1 over the square root of x squared. And what we're going to do is we're going to look at the ratio. Now, which one do I want to have up top? I want to have a nice denominator, right? So what do I divide by what to get a nice denominator?
I'm sorry, are you looking at the actual function or the bounds?
So I'm looking at this function right here and this function right here. I'm going to divide one function by the other and then consider their limit as x goes to infinity. I want to have the quotient to have a nice denominator, because in fractions, usually having a nice denominator is better than having a nice numerator, right?
So would that mean you should divide by the first integral that you wrote, x squared?
Good.
1?
Yes.
Okay.
So I take 1 over the square root divided by x squared, and I divide by 1 over the square root of x squared plus 0.1. And the way these work is that that's equal to the limits as x goes to infinity of the square root of x squared plus 0.1 divided by the square root of x squared. Now I can write this as a single square root, right? And then what do I get inside of the square root?
X squared plus 0.1 over x squared?
Sure. And then what does that simplify to? So that reduces nicely, right?
It's just 0.1.
No, that's
No,
not how
no.
fractions work.
No, I know.
No. 1 plus 0.1 over x squared, right? Now, what about limit laws? I can bring the limit inside the square root function because it's continuous. of 1 plus 0.1 divided by x squared, right? And what's the limit of 0.1 divided by x squared as x gets very big? X is like a billion.
Is that going to be 0?
Yeah. So that's equal to the square root of 1 plus 0. And so overall, I get 1, right? So when x is very big, the ratio that this has to 1 over x, it's arbitrarily close to 1. And that makes sense because this 0.1 doesn't really change the functional law, does it?
No.
So what
So-
have we, go ahead.
Oh, sorry. So just like the overall question is, it's like, so whenever you can't solve the problem by the p-test, you then divide by something that would make the denominator, or I don't know.
So you have two comparison tests at your disposal. Notice, by the way, that, for example, if you had sine, then the ratio comparison test doesn't work. The limit comparison test doesn't work. Why? Because sine goes from 0 to 1. And so the ratio does not exist in the limit because the ratio is oscillating as well. So sometimes you have to use a combination of the tests. The ratio test would not work in this example because the ratio is sine x. And what's the limit of sine x as x goes to infinity? It doesn't exist, right?
Right.
So this test is also sometimes useful. It's useful for getting rid of things like sine. And this test is useful because it gets rid of the annoying fact that, well, if the things are practically the same, but it just happens that their inequality goes in the wrong order, I still want to argue that they're approximately the same. And you can say that they're approximately the same by saying that the ratio tends to number that's between 0 and infinity strictly. So what does this say? This says that in the limits, f and g are approximately a constant multiple of each other, right? And I've established here that that constant is 1. Thus, since the integral from 1 to infinity of 1 over x dx diverges, so does the integral from 1 to infinity of 1 over the square root of x squared plus 0.1 by the limit comparison test. And I'll do a final example of this. So does the integral from, let's say, 1 to infinity of 1 over x squared plus 1 dx converge? Well, we actually evaluated this integral last time because the antiderivative is arctan, and so we can show that it converges. However, we can also show that it converges abstractly by using a comparison test. So what would we compare this to?
One over x squared.
Exactly. And as before, we'd like to have a nice denominator, right? So what do we divide by what?
Divide by the first integral.
Exactly.
So wait, quick question. So
Yeah.
the 1 over x squared, that's not from like a list of things that we can compare to, right? That's just like us knowing that that function is easy to solve?
Yes, because we have at our disposal the p-test, and the p-test tells us when integrals of this form converge or diverge, right?
Mhm.
So it's always good to compare two functions of this form because we know for a fact whether they converge or diverge.
Okay.
In general, you might have like sort of extra features in this function, like the +1. And the features might not change something like the limit of the ratio, but they might make it more difficult to find an antiderivative. In this case, the antiderivative is arctan, so we could just evaluate the integral directly to show that it converges. But abstractly, we can do a comparison to this function as well.
Okay. So basically, this test just builds off of the p-test.
You can compare to other functions as well. You can take a function that's you can compare to something that you can integrate directly.
Okay.
So it just has to change from a messy function to a nicer function.
Gotcha. Okay. Thank you.
In both of these examples, the nicer function happens to be something that can be resolved by the p-test. But I mean, I could even change the bounds and then arguably the p-test wouldn't apply. But it sort of does if you just move the 1 to a 2. But anyway, you're only going to be asked 2 examples of this on your homework, right? And it's not going to be on the final, so let's not worry about it too much. That's not a good thing to say when I'm covering the material, but also priorities. Okay, well, the same thing happens as before. We get x squared plus 1 divided by x squared, which is equal to the limits as x goes to infinity of 1 divided plus 1 over x squared, and that's equal to 1. So since integral 1 to infinity 1 over x squared dx converges by the p-test, so does the integral from 1 to infinity of 1 divided by x squared plus 1 by the limit comparison test. Okay, and that officially finishes all of the material for this course. So now we will do a review session, but let's take a break first. Any questions about that?
So this is all part of like a theorem, right? That you
There are 2 theorems that I cited, right?
Right,
These 2
yeah.
comparison tests.
Right. Okay. And okay, got it. Thanks.
So I didn't prove them, but they both sound reasonable, don't they?
Yeah.
The direct comparison test much more so than the limit comparison test, but you can prove it. In the limit, it's so the general intuition is that the functions are nice. So the problem isn't integrating on any finite segment, it's integrating on the tail. And if you can say something about the behavior of the functions for very large values, then that's where the problem or lack of a problem may occur. And so you can make conclusions from one based off of conclusions from the other.
That's where this would help.
Okay. Let's take a break until, so I want to have enough time to do the review session. Well, we have 2 hours to do the review session, so that's good. We're on good terms. Let's take a full 15-minute break. So break until 7:35. And then review session. I wanted to discuss complex numbers, but I think I probably won't have time to do that. So, or maybe just 10 minutes at the end, but mainly the review session. Okay, see you in 15 minutes. Okay, I'll get started. So first off, let me make a general remark that's looking at the homework assignments, and particularly for the people who have been coming to my office hours, I am convinced that calculus has been taught this semester and that a large number of people have actually learned some substantial things about calculus. So that is good. So we spent a semester studying calculus, and a good number of people actually learned an appreciable amount of calculus, which was my goal. Now let's just quickly recap what it is that we learned. So we started off by giving integration a definition. This was in terms of Riemann sums. Riemann sums, I will allow them to die. They will not be on the exam. And then let's see what the next interesting topic that we had was. So we discussed the statement of FTC1. And you don't have to memorize the statements, but I'll just remind you what the sort of trajectory of the material was. FTC1 says that if f is integrable on some closed interval a, b, and capital F is continuous on the same interval with the derivative of capital F equaling f on the open interval, then as far as we are concerned about this problem of finding the definite integral from a to b of f of x dx, that's answered by just taking this function and evaluating it at both endpoints. And another way to write this is to say f of x, then write a horizontal bar and write from a to b. So for example, finding the integral from 0 to 1 of x squared dx with Riemann sums was hard. However, we can notice that what's the antiderivative of x squared?
X to the third over 3.
Yep. So if we take this function and we take its derivative, then that's x squared. So by FTC1, since this is an antiderivative, we have that the integral from 0 to 1 of x squared dx is equal to this antiderivative evaluated between the points a and b, or 0 and 1. And that gives us 1/3 minus 0 equals 1/3. And bam, that is much easier than it is with finding it with Riemann sums. And so what FTC1 tells us that's finding antiderivatives is important. So this is the theorem which it explains why it is that we're always finding antiderivatives in this course. FTC1 tells us why antiderivatives are important. And then the recap of this would be, remember how hard it was to compute the integral of x squared from 0 to 1 using Riemann sums? Well, antiderivatives solve the problem for you. So now we're going to spend most of the rest of the course finding antiderivatives and then doing a bit of applications at the end. And so that brings up the question of how do we find antiderivatives? Well, these integrals with bounds, integral a to b of f of x dx, is called a definite integral. Now, on the other hand, the integral without bounds of f of x dx This is an indefinite integral. And this expression refers to some antiderivative. And we spend a lot of time computing indefinite integrals as well. So we've motivated the computation of antiderivatives. And so we define this notion of an indefinite integral to just be some antiderivative of f. And we give some results about how to find antiderivatives. And those are all of the integration techniques that we learn. So how do we find antiderivatives? Any questions to this point? And the answer to this is there are several ways. One is we can pull them out of thin air. So we can notice that capital F prime is equal to F. And now, of course, there is a show your work principle in this course. And so often just giving the answer and then observing that its derivative is your original function is not allowed, because where did you find the answer? But we motivated this by saying that you have a calculus A toolbox. In your calculus A toolbox, you have all of these basic functions. And your basic results are that each one of those basic functions has a derivative. And then you have linearity of differentiation. And then you have product rule, and you have chain rule. And so each one of those becomes a basic integration rule or a basic integration theorem. Now, all of your derivatives of your basic calculus A functions become sort of basic integrals that you have to memorize. So you have to memorize 11 integrals that come from derivatives of the basic calc A functions. And those calc A functions, so I'm giving you the calc A functions. These are the functions. So in other words, these are the answers to these are the answers to the integral of their derivatives. R. Then we have just power rule. So x to the r. We have the logarithm of x. We have e to the x. And then we have a bunch of trig functions. The rest of them are trig functions and inverse trig functions. Then we have, there are 6 basic trig functions: sine x, cos x, tan x, secant x, cosecant x, cotangent x, and then 2 inverse trig functions. So we will only care about 2 inverse trig functions in this course, as far as memorizing their derivatives goes. And those are arcsine and arctan x. So for example, if we ever have the square root of 1 divided by the square root of 1 minus x squared dx, then it's one of the basic formulas that this expression right here is the derivative of arcsine. And the other thing that I haven't mentioned is that if you have an antiderivative and you add a constant to it, then you also have another function that's an antiderivative, because the derivative of a constant is 0. So there's this conspiracy by calculus teachers worldwide that are going to require you to write plus c after every indefinite integral. Now, it doesn't have to be this way, but we're all in on it. And so you have to write the plus c. The justification is because if you have an antiderivative and you add a constant to it, you get another antiderivative. So this is the more general expression. Now, there are several things that are wrong with that sentence. For example, I mentioned earlier today, if you look at 1 over x and you look at the antiderivative of log x, the constants can actually differ from one piece or the other piece if the antiderivative isn't continuous everywhere. So it's a bit more subtle than that. All antiderivatives differ by constants only if you consider continuous antiderivatives on a closed interval. Anyway, that's apart from the side, you have to remember to write the plus c. So by inspection, you just have these 11 integrals which you've memorized. Now, there are some other integrals later on. We added a few more integrals that we could solve by inspection. It's the inspection list. So all of these can be justified by doing substitutions, but they're sort of boring substitutions. So we skip a boring substitutions. And so the integrals that you're allowed to solve by inspection are integrals such as the integral of 1 over x plus a dx. What is the antiderivative of this expression?
Log x plus a.
Yep. So you could justify this by making the substitution u equals x plus a, and then you have 1 over u du, and then you get this. But you shouldn't do it at every step, and this integral comes up very often in partial fractions decompositions. So we just do it in one step. Now, a related integral to this is an integral of the form x plus a to the r dx. So r does not equal to -1. What's the antiderivative of this?
X plus a to the r plus 1 over r plus 1.
Yep. So I'd say the prefactor first, 1 over r plus 1, x to the a to the r plus 1. And then the final integral that we can solve by inspection, it's also done by substitution. What if we have, so it's either cosine or sine, but let's say we're integrating cosine, and let's say we're integrating cosine ax dx. Well, then the antiderivative of cosine is sine. So what if I considered sine of ax? And what if I took the derivative of sine of ax? Well, then I'd get cosine ax, and then I have to use chain rule. So I'd get a cos ax, right? So right now, this is wrong because the derivative of this is a cos ax, but I can fix that by dividing by a, right? Similarly, the integral of sine of ax dx is equal to -1 over a cos ax plus c. And so these integrals came up when we were, for example, integrating cosine squared. We'd use a trig identity and we'd write it in terms of cosine 2x. And then it's sort of boring to do a substitution. So all of the 4 of these integrals you can solve by inspection, just because we're going to observe that these are the antiderivatives. And you can easily verify that these are the antiderivatives by differentiating these expressions. So you are also allowed to solve the following integrals by inspection. I haven't actually explicitly said that you can do this before in the course, but I sort of started using it in lecture. And so I'm just going to make it explicit right now. These integrals are perfectly fine to solve by inspection, right? The most non-obvious integrals under your basic formulas are arcsine and also arctangents. What's the derivative of arctan?
Over 1 plus x squared.
Exactly. So these are the most non-obvious ones. All of these have trig derivatives. So for example, the derivative of tangent is secant squared. So the integral of secant squared is tan x plus c. But these ones are a bit surprising because they're not trig functions. One's a rational function and the other is square root of 1 over a square root of polynomial. So these are the two genuinely surprising ones that you have to remember. And again, these come up often, this one especially 1 over 1 plus x squared. That comes up in partial fractions decompositions a lot. Okay, so this is first method for finding antiderivatives by inspection. What's the second method? Well, I'll just state this. It's sort of obvious. It's almost too obvious to state. We have a linearity of integration. So we have, for example, that the integral of f plus g, f of x plus g of x, dx is equal to the integral of f of x dx plus the integral of g of x dx. And that the integral of a times f of x, where a is a constant, is equal to a times the integral of f of x dx for a constant. And where do we use this? We use this, for example, for evaluating integrals of sums, and often we take prefactors and move them outside of the integral. So often, if you have numbers in front of an integral, you can move the numbers outside. We often move numbers outside just to forget about them. Okay, so these we use all of the time implicitly. Let's get on to the first beefy method. The first beefy method is substitution. And substitution comes from chain rule. So to remind you what chain rule says, and by the way, you should know how to differentiate things on this for this exam. Differentiating also comes up very frequently, right? We haven't, what we did in calculus A is still applicable, particularly finding derivatives. If we have f composed g of x, this is another way to write f of g of x. And if we take the derivative of this, then that is what's the derivative of f of g of x.
The chain rule, prime
Yeah.
g of x times g prime of x.
F prime of g of x times g prime of x. Exactly. Thanks. So this is the chain rule. And what does that tell us about antiderivatives. It tells us that the derivative of f composed g is this. So f composed g, or f of g of x, is exactly the antiderivative of the integral of f prime of g of x times g prime of x dx. Okay, but how do we actually write this? Forget about this form. Here's the better form, actual form. Suppose that f of u is equal to the integral of f of u du. Then if we have the integral of f of g of x times g prime of x dx, then if we have this, this is a bad grammatical construction. Just then this is equal to, so if f is this antiderivative of f of u, then that's the f in this case. So the antiderivative is f of g of x dx. Now, what does that tell us for a method? That tells us that in order to find this integral f of g of x times g prime of x, first we first solve integral f of u du, and then plug in u equals g of x to find the answer. And again, this is justified by FTC1 because it's an antiderivative. Well, it's not. It's actually just the definition of an indefinite integral. The definition of an indefinite integral is an antiderivative. And chain rule says that this f composed g is an antiderivative of this expression. Right? Okay, but now how do we actually use it? There's a special notation for using this. We use this with a special notation. So what happens is if we ever encounter the integral of f of g of x times g prime of x dx, then what do I write? I write in square brackets, let u equal what?
G of x,
Yep. And then what is du?
G prime of x.
G prime of x dx. Right? And then once I write that, I write the equal sign. And so what is this equal to? It's equal to the integral of what?
F of u du.
Yeah. And if you actually look at this, then you have an expression here, g prime of x dx. Well, that's equal to du, right? And I have f of g of x. So this is my u and this is my du, right? So it exactly follows that this checks out. And then once I solve for the integral in terms of u, I have to substitute back for x. Now, for definite integrals, we do not substitute back. Instead, we change the bounds when we substitute. And so the way that that works is, suppose that we have the integral from a to b of f of g of x times g prime of x dx. Then I write the same thing. I'm making the same substitution. So an indefinite integral is a function. It's an antiderivative, right? And on the other hand, a definite integral is just a number. So this expression right here, the type of expression it is mathematically is that it's just a number. And so if I write that this number is equal to another number, those two numbers have to be equal. And those two numbers will not be equal unless I change the bounds. So in order to actually have a true equality of numbers, you need to change the bounds. And the bounds become g of a and g of b. And then when you solve this integral, you'll just get some number. And then there's no back substituting involved in a number because it's just a number, right? Any questions about this point? I'm about to do some examples, but here's just the theory of substitution. So I will give you a warning. All of the examples that I'm doing are going to be just the examples that I did in lecture. It was pretty hard to produce all of those examples. So this is just a recap. I did not produce a brand new set of examples for this. So let's do an example. And right now I'm just going to do basic substitutions. I'm not going to do trig substitutions or more fancy stuff. The most basic substitution problem, this is arguably the simplest substitution problem in existence, is the integral of 2x divided by x squared plus 1. What substitution do I make to solve this problem?
Let u equals x squared plus 1.
Yep. Then what is du equal to?
2x dx.
Good. Thanks. So this is an example in which I have a ratio of two things, and the derivative of the denominator is equal to the numerator. In all of those situations, you just make a substitution of u equals the denominator, and what you get is that this is equal to, well, 2x dx is du, and 1 over x squared plus 1. Well, x squared plus 1 is u. So this is equal to 1 over u du, and that's equal to logarithm of absolute value of u plus c. And now the thing is that this is an unacceptable final answer. I need to write the answer in terms of x because I want a function of x. And so the last step is that I write that this is equal to logarithm, and then I substitute back absolute value of x squared plus 1. Well, the absolute value bars are redundant because this is always positive, but it's okay. We can leave them here. And that's the final answer.
So this is kind of a generic question. When can you get rid of the absolute value bars? Is it just like whenever it's positive, it wouldn't make sense to have it, or is there a certain rule?
Yes. So the absolute value bars, the definition of the absolute value function is that if it's positive, then it's just the original arguments. And if it's negative, then it's negative, the original argument. So the absolute value of orders might do something. They might be necessary if you have a negative argument, right?
Mhm.
But x squared plus 1 is always positive because you're adding a square, which is always non-negative to 1.
Okay, so this case, it would just be that it doesn't matter.
Yeah. So I could also write equals to log x squared plus 1. Now, I was aware of the fact that it was equal to this in the course, but I sort of glossed over it because I didn't want to confuse you. Right. Now, here's another example. What if I have something like the integral of sine to the 5th x times cos x dx? So here's another easy substitution problem. What substitution do I make?
Sine x.
Yep. What is du equal to?
Cosine x.
Yep. Dx. So that's good. I have cos x dx here. I have cos x dx here. Excellent. So I get integral u to the 5th du. And then if you just compare, look at what this expression is, u is sine x. So that's sine to the 5th. What is du? Du equals cos x dx. So I exactly recovered that original expression. You can see how these two lines are related with these substitutions. And well, okay, it's polynomial. I get 1/6 u to the 6 plus c. And then I substitute back to get 1/6 sine to the 6 x plus c. Easy peasy. Okay, so this is your core skill set. Remember when I said that for the final exam, it's you should prioritize on understanding the basics before you move on to more advanced material. This is some really basic material. You have to ensure that you have this stuff down pat come the oral exam. And there are going to be some questions like this on the basis problems. Okay, so these were just really some really basic substitution problems. I'll do definite integrals maybe at the end. I don't have, I'm going to just generally ignore definite integrals. They come up a lot in volume problems because those actually have bounds. Okay, after we do substitution, what's the next technique? What's the next technique that we studied?
Partial fractions.
But before that, we did another thing that started with P.
By parts.
Yeah.
By parts, yeah.
So integration by parts. And this comes from the product rule. And what does the product rule says? It says that if I have the function f times g, well, first off, f by writing a dot here, I just mean the product of f and g. So f of x times g of x. It's different from the composition circle, it's just a dot. Okay, well, the derivative of f dot g is equal to what? By product rule.
F prime times G plus G prime times F.
Exactly. Okay, so let's see what happens when we integrate this. That tells us that f of x, g of x, that's the antiderivative. This is an antiderivative of the integral of f prime of x, g of x, plus f of x, g prime of x dx. And how we rearrange this is that we use the linearity of integration on this thing. And we pull one of the integrals to one side. And so what we get is that the integral, and then let's write it like this, f of x times g prime of x dx is equal to, so the antiderivative is this function, f of x times g of x, minus the antiderivative of another function, and that is f prime of x times g of x. Now, so this is just outside of an integral. So this part is already solved once you've gotten to here. And you write one integral in terms of another integral. What goes on between one integral and the other integral? Well, you can consider it like transferring a derivative from one term in a product to another term. So it's not like a formula for integrating a product. It doesn't always work. It doesn't always lead to a place that's useful. Again, integration is not direct. There's no general formula for integrating a product. But you do have a formula that lets you transfer a derivative from one term in a product to another term at the price of just introducing a cross term outside of an integral. But as far as solving integrals go, that's okay. Now, there's a notation for this. Suppose that u is equal to f of x, and that v is equal to g of x. Then du is equal to f prime of x dx, and dv is equal to g prime of x dx. And so what happens is that the rule can be said as, well, f of x, that's u, and then g prime of x dx, that's dv, is equal to uv minus integral v du. And so this leads to a certain mnemonic. And when we apply parts, we use that mnemonic. So in particular, how do we apply it? What we do is to apply parts, we start off with the integral of f of x g prime of x dx. By the way, how am I doing for time? Okay, I have an hour and a bit left, an hour and 8 minutes. So I write again, a square matrix when I'm typesetting it. I typeset this like I would a matrix. And then I write u is equal to what?
F of x.
Yeah. And then I have this dv. What is dv equal to?
G prime of x.
Dx. Okay, so I start off with the top line of the matrix, and this top line is what I have right here. So this integral should be u dv. If I look at it, f of x times g prime of x dx is exactly what I have here. Now, what I do is I differentiate this function and I integrate this function. So now I write what du is. So you can imagine the top line is being transformed into the bottom line. Du is equal to f prime of x dx, and v is equal to what?
G of x.
Exactly. And then what I do after I write this matrix is that I write this is equal to. Now I look at the matrix and I look at this diagonal right here. And I take the product of those two things. And so I write the product uv, that's f of x times g of x. I call this the cross term. It goes across in this matrix. And then you write minus, and then you write the bottom term, minus the integral of v du, minus the integral of g of x times f prime of x dx. Well, you don't have to order them in this way. You can order them in whichever way you want, but this is what you get. So this is the notation for using parts. You write u and dv in the top, then you differentiate one, you integrate the other. So let's do some examples. Any questions about this notation? So not every single calculus class uses the same notation system. I spent quite some time thinking about what notation system I would use, and I found that this system of writing square brackets and then writing for substitution lets u equals du, and for parts this is, I think, the clearest notation system that exists for indicating when you're doing substitution and when you're doing parts. It's an ambiguous which method you're applying, and you can just fill this out and then follow it to realize what you're supposed to write on the next line. So I feel pretty good about this notation system. This is how you should write your work when you're doing substitution parts. Okay, let's do some examples. So again, these are examples directly from the notes. Here is the simplest example of integration by parts in existence. The integral of x e to the x dx. So of those two multiplicative factors, what do I want to differentiate?
E to the x.
But then I'd be integrating x, and then I get an x squared, right?
So it would just be x.
Yeah, you want to differentiate the x, y, because when you differentiate the x, you get a 1, and the e to the x is easy to integrate. Because then what you're doing is, if you have like a polynomial times e to the x, if you differentiate the polynomial enough times, it goes away. And right now, the reason that we can't integrate this directly is because we could integrate e to the x. But it's not e to the x, it's e to the x times a polynomial. Now, how do I deal with that polynomial? I can deal with the polynomial by differentiating it enough times, and then it becomes a constant. And I just have the integral of e to the x, and then I'm done. So that's why in this example, I want to differentiate the polynomial. Now, there are some times that you want to integrate the polynomial. We saw several examples of this, but in this case, what works is this. So du is equal to dx. And what's the integral of e to the x?
E to the x?
Yeah. And then in this notation, we don't write plus c, it's just a specific antiderivative, and we want to take the simplest antiderivative that there is. Constants would just make this more difficult. Okay, so I write that this is equal to, I write the product of the diagonal. So this is x e to the x, that's the cross term, minus the integral of e to the x dx. And what is that equal to?
X e to the x minus e to the x plus c.
Yeah. Okay, so that's the easiest example by parts. Again, this is the core basic material. So if you're going to prioritize learning something, learn this. And then let's do a bit of a more elaborate example. Let's say we have the integral of the logarithm of the absolute value of x divided by x dx. So what do I want to integrate and what do I want to differentiate? One of the two works.
We do log x.
Yeah, because it's hard to integrate log, right? The integral of log isn't an elementary function, so let's just differentiate the logarithm. On the other hand, what's left over, dv is what?
X dx.
It's not x dx, it's
1 over x dx.
yeah. Okay, now this is something that's easy to integrate. We know how to integrate this. We know how to differentiate this. Du is equal to what?
1 over x dx.
Yeah. So the derivative of log absolute value of x is 1 over x. I put the absolute value bars for more generality. Then we know how to integrate 1 over x. That's logarithm of the absolute value of x. Okay, now what do? We write the cross term. That's log squared of the absolute value of x. Then we write minus, and then we write the bottom term. And what do I get here? I get log absolute value of x divided by x dx, which is back to where we started, right? Now, how do I deal with this?
You can add that whole integral to the original.
Yeah.
side.
I bring this to the other side, and so I get that twice this integral. Is equal to log squared of x. And so this integral is equal to 1/2 log squared absolute value of x plus c. So this sometimes happens in parts. And then another example is that sometimes you have to do parts multiple times in a row. So if I, for example, had x squared eats the x, then I'd have to do parts twice. I'd have to differentiate that x twice.
Quick question. So
Yep.
we just added that second term over to get 2 integral log x over x. So how are you supposed to know when to do that, or if you just messed up your substitutions you made at the first part? Is it just because of the exact same thing that's why you do that?
Well, so assuming that you did the substitution correctly, let's suppose that you did the substitution correctly and you got to this expression, right? Then the question is, your goal is to find this integral. And if you have this equality, using this equality, you're able to evaluate the integral. So if you have this equality, that's enough information to find out what the integral is. Why? Because I can bring this over to the other side and then I can divide by 2. So having this equality is good enough to solve the integral. So if you're able to get this, if you're able to recover the original integral, then you get an equation which you can solve for what the antiderivative is.
Oh, okay. Okay, that makes sense. So it depends on what you're looking at. And in this case, that's why that works.
Remember what my syllabus said. This calculus is not about calculus. Calculus is about being a math gauntlet. You're supposed to learn a bunch of tricks. So it's about how do I find an antiderivative? Well, finding an antiderivative is a complex process. There's no straightforward way to do it. You have to do a bunch of tricks. Well, one of the things you do is, if I get to this situation, then I can use a trick. I can rearrange, right? So it's just a trick. It's one of the tricks that lets you solve an integral. Your goal is to find a solution to the problem. There's some sequence of tricks that'll get you to the solution because I'm posing it. It's not an impossible problem.
Okay. Thank you.
Yeah. So this is a trick in your toolbox. Everything that I'm discussing, every single example that I discussed today is to exhibit a trick that's in your toolbox. Okay. So these are the 2 examples that I have for partial fractions. Remember this notation. And then the next thing is the other thing that starts with a P. So that was 4. Now we do 5. And this is partial fractions. And so I could, well, okay, I'll say one thing. Partial fractions is a general method. This is how you do the integral of any rational function. Any rational function. Where a rational function is a ratio of polynomials. So for example, consider the integral. This is the example that I'll work out of x cubed plus x plus 1 divided by x squared minus 2 to the x minus 3 dx. So what is the first step in massaging the expression inside of this integral? What's wrong with this expression at the moment? What can we do to simplify it?
Would you do long division here?
Yeah, exactly. So in general, if you have f over g, these are polynomials with, and polynomials have a degree, right? The degree is the power on the highest non-zero term, with degree of f is greater than or equal to the degree of g. Then by doing polynomial long division, we can write it as so some quotients plus the remainder divided by g, where degree r is less than the degree of g, strictly less than. So in our example, what do I mean by this? What I mean is 3 is bigger than 2, right? So what I'm going to do is I'm going to start by dividing x squared minus 2x minus 3. And then I'm going to write this. This does not have an x squared term, so I'll put a 0x squared. Plus x plus 1. And you have to write out the polynomial long division. On all of your exams, when you didn't write it out, I took off a point and I said you have to write out the polynomial long division. And for the exam answers, I actually typeset the polynomial long division. It turns out there's actually a LaTeX library that does it automatically, that typesets the polynomial long division. You just give it the polynomial and it typesets it for you. But anyway, you have to write this out by hand, unless you're typesetting it. And so how do I do this? What do I multiply this by to cancel the highest order term?
X.
Yeah. Then I get x squared minus 2x minus 3. X cubed when I multiply by x. Let me erase that. Minus 2x squared minus 3x. Also, I do not have enough of a diversity of colors. I am unhappy about that, so I'll add some colors. Okay, so when I'm subtracting this, here I get a 2x squared. Here I'm subtracting minus 3 from x, so I get a 4x, and then I bring this one down. Now, what do I multiply this by in order to cancel the leading term?
2. X.
Well, that gives me an x cubed. I want to get rid of 2x squared.
Would it
Would
just
just be 2 or no?
Yeah, just 2. So when I take this and I multiply it by 2, I get 2x squared. Notice that the multiple I'm choosing is to cancel the leading term. Now, minus 2 times 2 is minus 4x, and then minus 3 times 2 is minus 6. And so when I subtract those, 4 minus minus 4 is 8x. 1 minus minus 6 is 7. And so what does that tell me? That tells me that x cubed plus x plus 1 divided by x squared minus 2x minus 3 is equal to x plus 2 plus 8x plus 7 divided by x squared minus 2x minus 3. So notice that the degree of the numerator now is 1, and that's less than the degree of the denominator. So before I actually do the partial fractions decomposition, I have to do a long division if the degree of the numerator is greater than or equal to the degree of the denominator. And this is how you do partial fractions. This is a trick in your toolbox. You saw it in high school and you have to be proficient in this trick. It is a trick. This course is about tricks. You have to do the tricks. You have to do the problem solving. Any questions about that? Okay, now how do we deal with this expression? 8x plus 7 divided by x squared minus 2x minus 3. What's the first thing that we do with it?
Factor out denominator.
Exactly. And how does it factor?
X minus 3 and x plus 1.
Exactly. Good, thanks. Now, so the general method for partial fractions is, I'll give you a more general example, but in this specific one, I guess that's not the general method. In this specific example, our two fractions would be a divided by x minus 3, or 1 divided by x minus 3. That's one of the things. And then b divided by x plus 1. So the general theory is that there are, if you look at any possible degree 1 or less term here, then it's possible to choose a and b such that you get anything. So there's some way to write this in terms of these two functions, in terms of multiples of these two functions, the sum of multiples of these two functions. That's the theory. And how do we do it? Well, I taught you one way about like subbing in numbers. That's a bit of, sometimes that method is quicker, but it's more theoretical. The robust method, which will always work, is to make it into a system of linear equations by cross multiplying. So we can write this under a common denominator. I have to multiply this by x plus 1 to get that in the denominator. Plus b times x minus 3 divided by x minus 3 times x plus 1. If you want to do the other method, then you're welcome to. And you don't have to solve a system of linear equations. It's arguably more robust. It leads to fewer errors, but it's the clever method. Whereas you can make a mistake solving and then cross multiplying, etc. Well, okay, we can rewrite this as, let's group the x term and the constant term as a plus b times x. Then we have a plus a minus 3b. Now I compare this to what I have here. If this is equal to this, the denominators are the same. And so the numerators have to be the same. And two polynomials are the same if their coefficients are all the same. So I get a system of linear equations from this. Let me make my page bigger. So then from this, I use this. Remember that you should not make a mistake of writing equality and implication. This is a string of equality. These things are all equal. This is because there exists some a and b such that this holds. Anyway, from this, I can conclude something that's not something that's equal to this. This is a statement of mathematical thoughts. And then I'm from this concluding another few mathematical thoughts. And those mathematical thoughts are that a plus b is equal to what?
X.
No, a plus b times x is equal to that. So a plus b is equal to, it's a number.
8.
8. And a minus 3b is equal to what?
7.
Yep. So how do we solve this? Well, I have that a is equal to 8 minus b, right? So I can write 8 minus b minus 3b is equal to 7. And that tells me that minus 4b is equal to 7 minus 8. That's minus 1. And that tells me that b is equal to 1/4, right? And that tells me that a, from this equation, is equal to 8 minus b minus 1/4. And if I write 8 under a denominator of 4, well, it powers of 2, 8, 16, 32. Minus 1/4. So I get 31 over 4. Right. So what does all of this tell me? All of this, everything that I've done. So I now go back to my original problem, which is to find this integral. Well, I didn't copy over the integral sign, but whatever. So this is equal to the integral of, well, what's the first thing that I did? First off, I took x plus 2 out of the integral. And then I looked at this expression that remained, and I wrote it as a times this plus b times this. A is 31 over 4 times 1 over what's x minus 3. And then plus 1/4. And what's the other one? It's x plus 1. And so when I integrate that, all of these are things that I can solve by inspection individually. What's my integral?
X squared over 2 plus 2x.
Yep. Yep.
Plus 31 over 4 log absolute value of x minus 3.
Exactly.
Plus 1/4 log of x plus 1. We'll see.
Good. Now imagine if I didn't allow you to solve these integrals by inspection and you had to do a substitution. That would be a complete waste of your time and it's boring. So these integrals, we have to allow you to solve them by inspection. It would just be against the Geneva Convention on torture otherwise. So yes, by inspection.
Sorry, the x plus 2 came from which part again in the first step?
Sorry, I didn't hear.
Where'd that come from again?
Well, what did we start off with? We started off with this expression, right?
Right.
With the greater numerator. So the first thing that we did is we did the long division, and so we were able to write it like this.
Oh, yeah, okay. Got it.
What does the long division tell us after all? It tells us that if we take this and we multiply it by this and we subtract it from this, then we get this, right?
Right, yeah. Got it.
So rearranging that gives us this equation. And in general, if we had a higher degree, then there just wouldn't be enough degrees of freedom to get something of degree greater than or equal to the degree of the denominator. That's why I have to long divide first. You wouldn't be able to solve this otherwise.
Also, just a quick question.
Hmm?
So if you have, like, when you're, like, after you do all that, the introductory stuff, like, when you're factoring out the denominator, or if you have, like, x squared plus 1, you can't do anything with that. So, like, because it's irreducible, do you have to, like, write out your partial fractions with, like, 2 different letters?
Yes, thank you. That's my next point. So I did an example in which I had simple terms and they were not irreducible quadratics, right? Now, something like x squared plus 1 has no roots. In general, if you have x squared plus bx plus c, then if b squared minus 4ac, so if b squared is less than 4c, then this has no roots. No real roots. Is irreducible. So how do you deal with irreducible factors? Well, let's suppose that you had something like some polynomial divided by, what's the example that I wanted? X plus 1 cubed times x times x squared plus 1. So this is fully factored because the irreducible quadratic is irreducible. So how do you handle higher powers? Well, you can handle that by writing a over what?
X plus 1.
Then plus b over
X plus 1 squared.
Yep. And plus c over
X plus 1 cubed.
Yes. So this is how you handle higher powers. Now, here's the thing to remember. If you have an irreducible quadratic, x squared plus 1, this has to, so notice how for every degree you get a letter. Well, this has degree 2, so you should introduce 2 letters. So you should say dx plus e. And so many people on the exam, incidentally, this letter was 0. It just happened that this was 0. But like a third of the class forgot that you had to include this. And in general, the system of equations might become unsolvable if you forget about this. So yes, precisely. If you have an irreducible quadratic, which you can tell by this discriminant test from the quadratic formula, then you have to remember to include this. So like a third of you forgot this on the exam. Thank you for reminding me to say that, although that was next to my notes. A third of you forgot about this. On the midterm. Oh, also, you have to show how you get this partial fractions decomposition. You would not believe how many people just pulled this partial fractions decomposition out of thin air. You have to show all of this work. Right? If I just started from this and I wrote that it was equal to this, that's not a solution. How I can't just pull this out of thin air. I have to justify it. How do I justify it? I justify it by doing the polynomial long division. You have to show all of your polynomial long divisions, and you have to show all of the methods by which you compute the coefficients in the partial fractions decomposition, right? That's necessary. So if you start off with an example like this, and you're being asked to integrate this, all of this is part of the work that you have to show for integrating it. So this is a fully worked out partial fractions example. Now, I want to mention one more thing. So this is a trick that comes up sometimes in partial fractions problems. It also comes up in some trig substitution problems. And so this is a lesson on completing the square. So this is another trick in your trick toolbox. This course is about tricks. Completing the square is a trick. You should know this trick. By the way, when I've been doing all of this material today, the earlier material is core material, so you should go as far as you can and ensure that you understand all of this. The most important material is the material that comes at the beginning, and then everything else builds on it. Let me open this up. Any questions about this, though? So partial fractions is good. And in some of the trig integral problems, for example, well, if you're doing the 300 IQ substitution, the magic substitution, the tan half angle formula, what that does is it transforms functions that are rational in terms of sine and cosine into just rational functions. And then how do you integrate rational functions? You do partial fractions. So your thought process, if you see an integral, by the way, on the basis problems, I will not tell you. This time, I will not tell you what method to use. I will just give a bunch of integrals, and you will need to figure out the method yourself. But how do you figure that out? Well, if you see a rational function, you think partial fractions, right? So to spice it up, I won't tell you the method. I have previously divided the methods up for a single type of problem, but we're going to make it spicy this time. Okay, completing the square. So suppose that I have something like the integral. Oops. of 1 over x squared plus x plus 1 dx. So if I look at this, well, the degree of the numerator is less than the degree of the denominator, so that's already done. And then I ask, is this fully factored? Well, I look at negative b squared, so that's 1. And then that's less than, sorry, b squared minus 4ac. 1 is less than 4 times 1. 1 is less than 4. So this has no roots. B squared less than 4ac. Well, a is 1 in this case. 4c is less than 0. Implies no roots. Now, what that means, if you have something that has a linear term, so there's an x here, I know how to integrate. Integral 1 over 1 plus u squared du, right? So the idea is that I'm going to take this integral and I'm going to write it in this form so that I can do my arctan trick. Actually, why am I erasing that? That's good to have. And so what I do is I complete the square. I'm going to write this. I look at these two terms, x squared and x, and I'm going to write this as x squared. So I'm going to add a number. What is that number?
The 2.
Sorry, I didn't.
2.
Well, okay. If I had x plus 2 squared, I'd get x squared plus 4x plus 4, right? But here I have x, so it's not 2. What is it?
1/2.
Yes. So in general, if I have x squared plus 2b, then this is equal to x squared plus b, sorry, x plus b squared. However, this equality is false at the moment. So if I look at x plus b and I write it out, I get x squared plus 2b plus b squared, right? So what do I have to do to fix this equality?
Subtract b squared.
Exactly. So now this is a true statement. So this is a true mathematical fact. So here I have x squared plus x. The thing is, this isn't of this form. One of the reasons it's not of this form is because I have this cross term, this linear term. So I can deal with the linear term by completing the square. Completing the square in general absorbs a linear term into a squared term. So because the coefficient here is 1, I take half of that coefficient, and that's the coefficient that I add. And in order to make this true, I should subtract what I've added here, the 1/4, and then I have my usual plus 1 dx. Well, okay, so carrying this over to here, continuing. This is in a different color, so this is just a side remark. It's not part of this. All of this should be in a different color. Now, what I have is the integral of 1 divided by x squared plus 1, x plus 1/2, sorry, squared plus 3/4 dx. Now, I'm going to factor this 3/4 out because I want it to be of the form u squared plus 1. So I can factor out the 3/4 here, all out fronts. And then I get 4/3 x plus 1/2 squared plus 1, right? So I've just factored this out. Okay, this prefactor becomes 4/3 integral. And now I'm going to take this 3/4 and I'm going to put it inside the square because I want it to be of the form u squared plus 1. So if I put that inside of the square, I get 2 divided by √3 x plus 1/2 squared, all squared, plus 1. Now this is of the form something squared plus 1. Sorry, this is dx. Now what substitution do I make?
Would u equal 2 over root 3 x plus 1/2?
Exactly. And yeah. Then my du is equal to
2 over root 3x. I mean 2 over root 3.
dx. Yeah.
Yeah.
Okay, good. So then if I look at what I have, my dx becomes root 3 over 2 du. So I have my 4/3, and then I also have this prefactor coming, and you should never forget about this. So that gives me a root 3 over 2. And I may as well put it out front. Now, if I look at this, this is 1 divided by what's inside the parenthesis, the outermost parentheses.
U.
Yeah, so u squared plus 1 du. Oh, but the main goal of why I did all of this completing the square thing was so that I could evaluate this integral. This integral I know how to evaluate. So the prefactor is 2 divided by root 3. And then what's this integral?
Arctan.
Yeah. And now I substitute back. And I get arctan. And then I may as well multiply this out, 2 over root 3x, and then this times 1/2 plus 1 over 3 plus c. Okay, so in general, if you're dealing with a quadratic, reducible quadratic that has a linear term, then you can get rid of the linear term by completing the square. That's what completing the square does. So completing the square gets rid of linear terms or absorbs linear terms into quadratic terms. And that's just that first step. The remaining steps tell you how to deal with the fact if it's a plus b squared u. So we deal with one by putting this out, and then we deal with the other by bringing that inside of the square. But we deal with the linear term by completing the square. So if you have a linear term, and you don't like the linear term and you want to do something like this, you complete the square. Now, I have an example from the homework. In one of the homework assignments, you were asked to do the integral of, so I'm not going to do the trig substitution, but it was something like, let's see, 4x squared minus 24x plus 27. And then this was to the power of 3/2 dx. So I'm not going to do this integral fully, but I'm going to tell you how you deal with this. And then there was written hint, complete the square. So if I have an expression like this, 4x squared minus 24x plus 27. First off, I can forget about this constant term. My first worry is to get rid of the linear term. So I only care about these two terms. I may as well factor the 4 out of just these two terms. Again, this constant term has nothing to do with it. We're just dealing with the linear term by absorbing it into the quadratic term. So that's where the action is happening here. Now there's a 4 out front, and the 4 is annoying, so I can just factor it out, and then I can work inside the parentheses, and I can forget that the 4 is there. I just keep writing it on the outside, right? So by taking the 4 out, I now have dealt with the problem that it's not 1x squared, but 4x squared. Now I'm just working inside the parentheses. So inside of the parentheses, I can write this as x what? squared.
-3.
Yeah, because this coefficient right here is twice this coefficient. So I just take this coefficient -6 and I divide it by 2 and I put this. Now, if I just left this term here, then this equality would be false. What do I have to do to fix it? So here I'm adding, when I expand this out, I get a +1.
+9.
Yes. And so the problem is that I have an extra +9 and I deal with that by doing what?
Add 3.
Subtracting.
No, subtracting 9. So I have +9. I don't want a +9. I subtract a 9. Now, what's inside the brackets? This is equal to this. And then I have my +27 as before. Good. So I've completed the square. So I've done that. And the way that I did that is I didn't like the fact that I had the 4 out here. So I just removed the 4. And then I'm just working inside the parentheses. The only thing that matters in the universe is what's inside the parentheses. The 4 just stays outside and it's out of my consideration. This is the same idea of like moving constants out of integrals. The integral, the body of the integral is more complicated than you need. Just move all of the constants out front and you can forget about them entirely. You just keep writing them out at the front. Okay. So if now I am expanding this out, so I get 4 times x -3 squared. Now, 4 times 9 is 36. So I have 27 minus 36. Now, how do I do this subtraction? Well, I can count up from 27 to 36. So 27 plus 3 is 30, and then plus 6 is 36. So that's a difference. The distance between those two numbers is 9, and 36 is bigger, so it's -9. Right? Now, if I want to write it of the form u squared plus 1, then I want to make this coefficient be 1. So I'll factor out the 9 out of everything. And so I get 4 divided by 9, x minus 3 squared minus 1, right? And now what do I do next? With this 4 9ths.
Would you multiply out and then distribute the 4 9s?
Well, I'm not going to multiply out. I deliberately factored it. So multiplying it out would just be undoing what I just did, right?
You take it out of the parentheses.
Or rather, it's already out of the parentheses. I'm going to do the opposite of that. I'm going to put it in the parentheses.
Oh.
So I'm going to put it in the square. So I can write this as 2/3 x minus 3 squared minus 1, right? So now look at this. This is, I've just taken this expression and I've written it in a very nice form. It's u squared minus 1, and then the 9 is out front, so it doesn't matter anymore, right? So I just started with this polynomial and then I put it into this nice form. And in general, if you're going to do some sort of trig substitution next, then, well, okay, if you were doing a trig substitution and you want to get rid of the square root, because this is the cube of the square root of this, right? What would I want to make? I would so my substitution would be let's u equal what? What do I want to replace this parenthetic expression with in order to get Pythagoras to work?
The 2/3 x minus 3 squared.
Well, sorry. Thank you. I do not want to write let u equal to. I want to write let x equal. Let x equal what? Sorry, no, not let x equal to. Let 2/3 x minus 3 equal what?
U? Is that what you're?
No, I'm doing a trig substitution.
Oh.
Oh, is it a secant u?
So if I have -1, then it would be secant, right? So in this case, A is 1. I put it inside, so I'd like this to be secant U. And then 2/3, I guess, dx is equal to secant tan. So this is a bit different from how I did it before. Before I would actually not mind having the coefficient. So actually, you know what? This is how we'd usually do it. How we'd usually do it in the case of trig substitutions would be to write this as we take the 4 out. And then we'd have x minus 3 squared minus 9/4, right? Then we do the substitution. Then we do the substitution, let u equal, let x equal x minus 3 equal to 3 halves secant u, which is the same as what I have before, except I put the 2/3 on this side. So when you're completing the square in order to write it of this form, x squared plus 1, if you care about the +1, then you'd do it like this, and you bring this inside of the square. If you're just doing a trig substitution, though, you could also do it like this, and then you could make this substitution, right?
I'm sorry, I'm just confused about the last step. So before you did like the green writing, can you just re-explain that last step?
So in this original one.
Yeah.
In the original one, let's suppose that I want to have a 1 here. So I know, for example, let's say I want to have a 1. Let's say I want it of the form u squared minus 1. I want to put it in this form. Well, then what I do is I like to have a 1 here, so I want to factor the 9 out. But I factored the 9 out of everything. Now the 9 is out front, and I can forget about the 9. I'm now only focusing on the thing in parentheses. Now the thing in parentheses already has a -1 here, so that's good. But it's not of the form u squared minus 1. It's of the form 4/9 u squared minus 1. So to make it u squared minus 1, I take this 4/9 and I bring it inside of the square, taking the square root of this expression. If I square this, then it's the same as 4/9, this squared times this squared, right?
Yeah.
So this is equal to this, right?
Yeah.
And in general, if this were equal to secant, then Pythagoras would apply. I could rewrite it as tan u, right? Tan squared u.
Oh, so just because you knew it was like a u squared minus 1 form, that's why you plugged it in as secant u?
Yeah. So that's the next topic that I'm going to discuss, trig substitutions, right? Or, well, rather trig integrals. The next part of the material is trig day, what I covered in trig day. How much time do I have? Oh, no, I have 17 minutes. So I'm going to just do a blitz version of trig integrals, and then that's going to be that. So the review today was about computing integrals. Okay. Blitz 17 minutes version of trig integrals, in which I'm going to describe this. So, okay, your question is going to be answered here. Before I talk about trig substitution, which are, by the way, my favorite thing in this course, trig substitutions. So I might be a bit biased and put a bit more of those on the exam and ask a bit more about them than I should. Let's just quickly describe the trig identities that you have to know. So you have to know these trig identities. Well, the most basic trig identity is Pythagoras. The other version of this, if we divide everything by cosine squared, we get tan squared plus 1 is equal to secant squared. So for example, if I have secant squared x minus 1, then I can rewrite that as tan squared. And that's why we do this substitution here, because this is to the power of 3 halves in the integral. And I'd like to get rid of the power of 1/2. That's like a square root. This is the cube of the square root. How do I get rid of that square root? Well, I write this as a square. How do I write it as a square? Well, if I make the substitution that this is secant, then this all becomes tan squared u. And then I get rid of the square root. So the overarching goal was to get rid of the square root. And how do I do that? I do it with tricks, right? And this trick works. Okay, so these are the two basic versions. You have to know Pythagoras, you have to know this. You also have to know double angle formulas. So cosine of 2x is equal to cosine squared x minus sine squared x. And then we can rewrite this in two ways. We can also write this as, well, if we write cosine squared as 1 minus sine squared, then we get 1 minus 2 sine squared x. Or if we write sine squared as 1 minus cosine, then we get 2 cosine squared x minus 1. And so these equalities lead to the following formulas. That cosine squared x is equal to 1/2 1 plus cos 2x. That's being a bit scrunched. I'll write it up here. 1/2 1 plus cosine 2x. And sine squared x is equal to 1/2 1 minus sine 2x. So in general, if you have an expression of the form cosine squared, there's two things that you can do with it, right? You can either write it as 1 minus sine squared, or you can write it as 1/2 1 plus cos 2x. You also have from Pythagoras cosine squared x is equal to 1 minus sine squared x. And depending on whether the powers are even or odd, if you have like a product of sines and cosines, you would either rewrite everything in terms of sines using this expression, or you'd use these formulas. So for example, if you're integrating cosine squared x, then which formula do you use? We have very little time, so let's get some answers if you want to review the. So you use this formula, right? Use cos squared x is equal to 1/2 1 plus cos 2x. On the other hand, what happens if you're integrating cosine cubed of x? Then what you do is you're going to use cos x dx dx as equal to sine as equal to du, where u is equal to sine x. But we'd like to rewrite the rest of it in terms of cosine. So I can rewrite the cosine squared as what?
The 1/2.
No, in this case, I'm not going to do that. As what?
Cosine squared.
1 minus sine squared, right?
I see.
So this is what I do with this even power. This is what I do with this odd power. And if I do that with the odd power, then what substitution can I make?
U equals sine.
Yeah. Then du is equal to cos x dx. And then what I get over here is that this is equal to the integral of 1 minus u squared du, right? And then I can solve that. So when you have something like cosine squared, you have two options. You can, well, sometimes you're happy. For example, if I inserted an extra factor of sine squared, then we wouldn't want to rewrite the sine squared. The sine squared is good. We'd have to write the cosine in terms of sines, and then we just have this one remaining odd power, and the one remaining odd power we absorb into the d to make a du. And then if everything else is written in terms of sines, we're good. Okay, so these trig identities are all useful. And then you have also the 300 IQ substitution. Let's say I'm not going to discuss this right now. I'll just remind you of what the formulas are. So you look these up. And then I'll have a question about the 300 IQ sub, and you would use these formulas when you're doing the semi-open book. So you wouldn't look them up online. You look them up, for example, here when doing the basis problems. If u is equal to tan x over 2, then cos x is equal to 1 minus u squared over 1 plus u squared. Sine x is equal to 2u over 1 plus u squared, and dx is equal to 2 over 1 plus u squared du. So when you do that substitution, these things happen. Okay, now let's get to my absolute favorite material in this course, and that is trig substitutions. And so if you have, let me just quickly expand the page. So if you have something like the square root of, let's say, 1 minus x squared, how can I deal with the square root? I could remove the square root. But using Pythagoras, if x equaled what? So I'm going to make it into a trig function that's going to let me rewrite this as a square using Pythagoras.
Like, is it the a secant?
Secant would be x squared minus 1. This one I would use
Sine?
Yes, sine u. Because then square root 1 minus x squared is equal to square root 1 minus sine squared u. And 1 minus sine squared, well, sine plus cosine is equal to 1. Sine squared plus cosine squared is equal to 1. So 1 minus sine squared is equal to cosine squared. And that's equal to cos u. So this substitution lets me get rid of the square root. And so there's a table that I use. And that table is, for some reason, not written out on this page, but really? Okay, but I remember it. If you have a squared plus, a squared plus x squared. So here is the table. If I have, I use. So what substitution do I make here? I make x equals so here I use a tan u. Here I use a secant u. And here I use a sine u. And all of these can be rewritten with Pythagoras, and then Pythagoras applies. And so I'm going to do an example of a trig integral. Yeah, no, I have the table here. It's up top. And then I'm going to discuss this final step of it. So suppose I have dx divided by x squared minus 9. It's the power of 3/2. So what substitution do I make?
Let x equal a secant u.
What is a?
3.
3 x squared minus a squared, so secant. Du is equal to 3 what?
Secant u tan u.
Oh, I made a typo. This should be x, right? Dx equal, dx is equal to 3 secant u tan u du. Okay, so what does my integral become? My integral becomes integral 3 secant u tan u divided by, now this becomes 9 secant squared u minus 9 to the power of 3/2 du. And then I can write this as, well, I can put this 3 out front, and then I have this 9 to the power of 3/2. Let's just bring those prefactors out front. So I have secant u tan u divided by secant squared minus secant squared u minus 1 to the power of 3/2 du. Then that becomes tan squared to the power of 3/2. By the way, this is 27. And then so I get 1 divided by 9. I can rewrite that like that. And then I get tan squared to the power of 3/2. So that becomes tan cubed u. And I can rewrite this as secant u, and then this tan crosses out with that tan divided by tan squared. And if I rewrite that in terms of sines and cosines, I get 1 over cos x, and then this is sine at the bottom, because it's tan at the bottom. Sorry, these are all u's. And I can rewrite that as 1/9. And then, so this cosine cancels that cosine. So I get 1 cotangent and then 1 divided by sine. So that's 1 divided by sine is cosecant u cotangent u. Oh, but I recognize this as minus the antiderivative of cosecant. Okay, now here is the punchline. So when I substitute back in, I get minus 1/9 cosecant of, now what do I get? Of arcsecant x over 3. But this is an unacceptable final answer. Whenever you have a trig function of an inverse trig function, you can rewrite it. And how do you rewrite it? So does everyone see why u is equal to this? Because if I solve for u, I get x divided by 3, and then I apply the function arcsecant, the inverse function, to both sides. Now I draw the triangle. So trig substitutions have all of this dynamic things, which end also in drawing the triangle. Now, arcsecant is secant is 1 over cosine. Cosine is adjacent divided by hypotenuse. 1 over cosine is hypotenuse divided by adjacent. So hypotenuse divided by adjacent is x over 3. So I put x as the hypotenuse, 3 as the adjacent, and then the opposite side becomes x squared minus 9. Then if I take cosecant of this angle, this is an angle such that its secant is x over 3. Then cosecant of that angle is 1 over sine. So it's hypotenuse divided by opposites. And so I get that this is equal to minus 1/9 hypotenuse x divided by opposites, square root x squared minus 9 plus c. So I rushed through that problem, but remember that you draw the triangle and you get this. So that concludes this example. And then I didn't do a 300 IQ trig substitution, but I had an example for that prepared. You can look that up in the notes. That covers all of the integration techniques that we have learned in this course. So that concludes my review. My review has gone through a blitzkrieg version of absolutely every single trig integration technique that we have learned in this course. Any questions? Okay, so that went very quick, and you can watch this on the recording, which I'll send as soon as I get it sent to me. And then again, as I mentioned before, I am satisfied that a bunch of you have actually learned an appreciable amount of calculus. Okay, and one more really important thing. So the course evaluation situation is weird because apparently none of us got an email about it. It is very important to me that course evaluations get filled out. So I'm going to remind you of this now. Then I'm going to inquire as to what's up, why haven't my students gotten course evaluation emails. But once that gets fixed, can you all please fill out the course evaluations? That's very important to me.
Yes.
Okay, thank you. And otherwise, okay, so hopefully you learned some calculus. And then if you want office hours on the weekend, you can send me an email and we can make a time. And then this review session should hopefully have been useful. Prioritize studying for the midterm over doing homework 5. Homework 5 is the shortest homework assignments. All of the questions, they're short questions. You don't have to do as much as you had to do in previous assignments. And I'll post the solutions for homework 4 soon. And then I won't post the solutions for homework 5 because it's not on the final exam. But you will have homework 4 reference solutions. And today we discussed how to integrate. And that is one thing that we learned in this course. Okay, so thank you all for attending my lectures and signing up for my course. I'm glad that you stayed. And again, I am convinced that you learned some calculus. So I won't say hopefully you learned some calculus. You did learn some calculus, and that's great.
Thank you.
Thank you so much.
Thank you.
Yay. Okay, so hopefully it was an enjoyable semester. Have a great rest of the summer and good luck in all of your future studies. And I will be seeing you all on the oral final exam. Ciao.
Have a good night.
Good night.